Alright, let's go. Number 10. The Singularity Problem. Karl Schwarzschild was not trying to break physics. In 1916, stationed on the Russian front during the First World War, sick with an autoimmune disease that would kill him within months, he sat down and solved Einstein's field equations exactly, for the simplest case possible, a single, non-rotating mass sitting alone in empty space. He mailed the solution to Einstein from a military hospital. General relativity predicts that mass curves space-time smoothly, continuously, everywhere. Gravity gets stronger as you approach a massive object. But the equations were supposed to stay finite. They were supposed to behave. At the center of Schwarzschild's solution, they did not. Density went to infinity. Curvature went to infinity. The equations simply stopped producing numbers that meant anything. Schwarzschild published this in a 1916 paper for the Prussian Academy of Sciences. For decades, physicists assumed it was a mathematical quirk, a flaw of perfect symmetry that would vanish in any real, messy, rotating star. Then in 1965, Roger Penrose published a paper in Physical Review Letters proving the opposite. Using topology instead of exact solutions, Penrose showed that under very general conditions, collapse to a singularity isn't a special case. It's unavoidable. He won the Nobel Prize for it in 2020. Physicists proposed a way out, the cosmic censorship hypothesis, the idea that every singularity is safely wrapped inside an event horizon, hidden from the rest of the universe. Nobody has proven it. Some solutions to Einstein's equations allow naked singularities exposed to the outside universe, and nobody can rule them out. So somewhere inside every black hole, including the ones astronomers photograph, sits a point where the rules that describe reality go quiet. Every atom that ever falls in is heading toward a location where physics has nothing left to say. Nobody has ever seen what happens next, only the equations that give up trying to describe it. Number 9. The confirmation, by pure math, of spaghettification. Kip Thorne and a generation of relativists working through Einstein's tidal equations weren't hunting for a horror story. They were solving a routine problem in differential geometry. How does gravitational pull differ across an extended object instead of a single point? Ordinary gravity, the kind that holds you to a chair, pulls almost identically on your head and your feet. The difference is too small to notice. Near a black hole, that difference stops being small. The math showed that as an object approaches the horizon of a stellar mass black hole, the force on the near side can become millions of times stronger than the force on the far side. For a black hole roughly 10 times the mass of the Sun, calculations place the point of fatal stretching several hundred kilometers before the horizon is even reached. A body would be pulled into a thread narrower than spaghetti, still alive, while it happened. This isn't speculation without observational backup. In 2012, Suvi Ghazari and collaborators published a paper in Nature documenting an actual tidal disruption event, a star torn apart by a supermassive black hole, caught in ultraviolet and optical light exactly where the equation said the shredding would begin. Some physicists hoped larger, supermassive black holes might be gentler, since tidal forces weaken with size. And the math confirms that too. An object could cross the horizon of a sufficiently massive black hole intact, stretching only after it was already inside, already unreachable, already unable to report back. No exception has ever been found. Every mass, no matter how it approaches, follows the same stretching curve to the same silent conclusion, somewhere no signal can leave to confirm it. Nobody has ever measured this happening to a human body, and the geometry guarantees nobody ever will. Number 8. White holes, the theoretical mirror. Martin Kruskal wasn't trying to invent a new object. In 1960, he was simply trying to write down the cleanest possible mathematical description of the region around a Schwarzschild black hole, extending the coordinates so they wouldn't break down at the horizon the way earlier versions did. Einstein's equations are time-symmetric. If you have a valid solution, running it backward in time is, mathematically, an equally valid solution. Applied to gravitational collapse, a black hole only pulls in, never releases. Kruskal's extended coordinates revealed something the original equations technically permitted, a mirror region that only ejects matter and radiation, and can never absorb anything, ever. Physicists named it a white hole. It sits in the same solution as the black hole, connected through a region some called an Einstein-Rosen bridge. The problem was stability. Later analysis, including work following from Kruskal's own extension, showed that any white hole exposed to even a single incoming photon would collapse into an ordinary black hole almost instantly. No astrophysical process has ever been observed creating one. Some cosmologists, working independently, floated the idea that the Big Bang itself could be reinterpreted as a white hole event, matter and energy erupting outward from a region nothing could re-enter, though this remains a fringe reading with no supporting data. Roger Penrose himself has speculated more recently about tentative and unconfirmed correlations in the cosmic microwave background that some have loosely associated with white hole adjacent ideas, correlations the broader physics community has not accepted. The equations that predict black holes, tested and confirmed by direct imaging, predict white holes with exactly the same mathematical confidence, and yet, in over a century of observation, not one has ever been found. If the math is symmetric and nature only kept half of it, the question is why the universe chose one direction and never the other. That mirror image object leads directly into something scientists still can't confirm was ever detected at all. Number 7. Hawking radiation. Still unconfirmed. Stephen Hawking did not set out to prove black holes emit anything. In the early 1970s, he was actually trying to refute a claim by Jacob Bekenstein, a graduate student who had proposed that black holes possess entropy proportional to the area of their horizon. Hawking thought the idea was flawed, since an object with entropy should also have a temperature, and an object with a temperature should radiate, and everyone knew nothing escapes a black hole. Applying quantum field theory to the curved space-time around a horizon, Hawking ran the calculation to disprove Bekenstein. Instead, he found that particle pairs forming spontaneously near the horizon could be split, one falling in, one escaping outward as real detectable radiation. Bekenstein had been right. Hawking published the result in 1975 in Communications in Mathematical Physics, Volume 43, a paper that quietly implied every black hole in the universe is slowly evaporating. The numbers made confirmation almost impossible. For a black hole with the mass of the Sun, the predicted radiation temperature comes out to roughly 60 billionths of a degree above absolute zero, thousands of times colder than the 2.7 Kelvin cosmic microwave background that fills all of space. The signal is drowned before it begins. Physicists have proposed detecting Hawking radiation from theoretical primordial black holes. Tiny ones formed in the early universe that would be hot enough to see, but not a single primordial black hole has ever been confirmed to exist. Laboratory analogs, using sound waves in Bose-Einstein condensates, have reproduced something resembling the effect, but an analog in a lab is not a black hole. 50 years after the original paper, the phenomenon that first suggested black holes might not last forever remains a prediction on paper, never once observed at the source it was written to describe. An entire field now assumes evaporation happens, built on math nobody has watched play out in the sky. Number 6. Frame dragging and the physics of a spinning black hole. Roy Kerr wasn't chasing anything exotic in 1963. He was working through an unsolved and notoriously difficult extension of Einstein's equations, what happens to space-time around a rotating mass, rather than the simpler stationary case Schwarzschild had already solved. The math is significantly harder, and for years no one had cracked it. Standard relativity already predicted that any rotating object should drag the fabric of space-time around with it slightly, the way a spinning ball dragged through honey twists the honey nearby. For something as gentle as Earth, this frame-dragging effect is a tiny, barely measurable smear. Kerr's solution showed that for an object as extreme as a spinning black hole, the dragging isn't a smear. It's total. Around a fast-spinning black hole, there exists a region called the ergosphere where space-time itself is dragged forward faster than light could ever move against it, meaning nothing, regardless of engine power, can hold still relative to the distant stars. Kerr published this in a short 1963 letter to Physical Review Letters. The gentler, Earth-scale version of his prediction wasn't measured until decades later. In 2011, Francis Everett and the Gravity Probe B team, writing in Physical Review Letters, confirmed frame dragging around Earth directly, measuring a drift of 37.2 milliarc seconds per year in gyroscopes orbiting the planet, matching Relativity's prediction closely. That confirmed the small case. The extreme case, the ergosphere around an actual black hole, has never been measured directly, only inferred from the behavior of matter and light in its vicinity. The theory suggests that within the ergosphere, a spacecraft could in principle extract energy from the black hole's rotation itself, a process named after Penrose, by falling in and splitting apart. One piece escaping richer than it went in. Near a spinning black hole, the geometry doesn't just bend around you. It moves, and it takes the meaning of standing still along with it. That distortion of geometry itself points toward an idea stranger than any single object, that the space you're standing in right now may not be fundamental at all. Number 5. The Holographic Principle. Gerard de Hooft wasn't trying to describe the nature of reality. In 1993, he was trying to solve a narrower, technical problem in quantum gravity. How do you count the maximum possible information that can exist inside a given region of space? Ordinary intuition and ordinary physics says information scales with volume. A bigger room can hold more books than a smaller one. Black hole thermodynamics, built from Bekenstein and Hawking's earlier work, had already shown something odd. A black hole's entropy, its total information content, scales not with its volume but with the area of its horizon, a two-dimensional surface. Et Hooft took that oddity seriously and generalized it. He proposed that this isn't a black hole quirk at all, but a fundamental limit on any region of space whatsoever. The maximum information any volume can contain is bounded by the area of its boundary, not its interior. Et Hooft published the idea in a 1993 paper titled Dimensional Reduction in Quantum Gravity. Leonard Susskind at Stanford developed it further, publishing The World as a Hologram in the Journal of Mathematical Physics in 1995. Arguing that everything happening in three-dimensional space might be fully and exactly described by information encoded on a distant two-dimensional surface, the same way a flat hologram encodes a three-dimensional image. In 1997, Juan Maldacena gave the idea its first rigorous mathematical proof in a specific type of curved idealized spacetime called anti-de Sitter space. It became the most cited paper in theoretical physics. The catch nobody has resolved: anti-de Sitter space is not the kind of universe we live in. Whether the holographic principle applies to our actual, expanding cosmos remains completely unproven, 3 decades after Hooft first wrote it down. If the boundary is where the real information lives, then everything inside it, including you, might be the shadow, not the source. The next 2 entries aren't calculations anymore. They're photographs. Number 4. Sagittarius A Revealed. The Event Horizon Telescope team wasn't satisfied after their first success. Having imaged a black hole in a galaxy 55 million light-years away, they turned the same planet-spanning array towards something much closer and, they assumed, much easier, the supermassive black hole at the center of our own galaxy, based on general relativity and on the earlier M87 result. They expected a similarly proportioned glowing ring, just scaled down to match a smaller mass. What they found instead was a target that fought back. Sagittarius A has roughly 4 million times the mass of the Sun, compared to M87's several billion, but material orbits it in minutes rather than days, meaning the source itself was changing shape while the telescope was still collecting data. Smearing every exposure, the team had to build entirely new imaging algorithms just to freeze a moving object long enough to photograph it. In 2022, the Event Horizon Telescope collaboration published the result in the Astrophysical Journal Letters, Volume 930, Paper L12. A glowing asymmetric ring, matching Einstein's century-old predictions with striking precision, sitting at the exact gravitational center of the Milky Way. Every star in our galaxy's central region, including, indirectly, our own sun's slow 25,000 light-year orbit, is arranged around this object. Some researchers have raised legitimate questions about how much of the final image depends on the reconstruction algorithms used to process fragmentary data from only 8 telescopes, since the same raw data, processed differently, could in principle emphasize different features. The collaboration addressed this with blind, independent teams producing consistent results. The ring itself is no longer in doubt. The exact center of the galaxy you were born in has now been photographed, and it looks precisely like a hole cut out of space. Number 3. The Event Horizon Telescope's first image of M87. More than 200 researchers across dozens of institutions weren't originally certain the project would work at all. In 2017, they linked 8 radio observatories spanning the planet, from Hawaii to the South Pole to Spain, into a single virtual telescope the size of Earth, attempting something no one had done, resolving detail fine enough to see the shadow of an event horizon. General relativity had predicted, decades earlier, exactly what that shadow should look like: a dark region encircled by a thin, bright ring of superheated lensed light. The team spent 2 years processing the data before releasing anything. On April 10, 2019, the Event Horizon Telescope collaboration published 6 papers simultaneously in the Astrophysical Journal Letters, Volume 875. The lead image showed a ring roughly 40 micro-arcseconds across, surrounding the supermassive black hole at the center of the galaxy M87. 65 million light-years away, with a mass later refined to about 6.5 billion times that of the Sun. 4 independent teams, deliberately kept blind to each other's work, reconstructed the same ring shape from the raw interferometry data, ruling out shared bias. The image matched Einstein's 1915 field equations, a theory built with no knowledge of black holes at all, with almost no room for deviation. This wasn't a discovery of something new and strange. It was the opposite, and somehow, that made it worse. A century-old theory, tested at the most extreme gravitational conditions physics can access, simply worked, precisely, on the first real attempt. Every unresolved paradox on this list, the singularity, the missing information, the firewall, now belongs to a photographed, confirmed, undeniably real object. The picture didn't answer any of the open questions. It just proved beyond doubt that the object asking them is actually out there. Number 2. Firewalls versus smooth horizons. Ahmed Elmhary, Donald Merolf, Joseph Polchinski, and James Sully weren't trying to overturn 30 years of consensus. They were testing it. Black hole complementarity, developed earlier by Leonard Susskind, Gerard Hooft, and John Preskill, proposed an elegant resolution to the information paradox. An observer falling into a black hole experiences nothing unusual crossing the horizon. Per Einstein's equivalence principle, while a distant observer sees that same information smeared and preserved on the horizon's surface. Both descriptions are true, the idea went, because no single observer can ever compare notes between them. In 2012, the 4 physicists, working through a careful thought experiment involving an observer named Alice, tried to confirm this consistency mathematically. It didn't hold. They found you cannot simultaneously keep 3 things true: that information is preserved, that ordinary quantum field theory applies near the horizon, and that an infalling observer feels nothing unusual crossing it. Pick 2. If information is preserved, they argued, the third assumption breaks, and a wall of extremely high-energy quanta must exist right at the horizon, instantly destroying anything that touches it. They published the result as black holes, complementarity, or firewalls in the Journal of High Energy Physics in 2013. The failure parade that followed has lasted over a decade. Samir Mathur proposed fuzzballs, horizons made of stringy structure with no interior at all. Juan Maldacena and Leonard Susskind proposed ER equals EPR in 2013, suggesting entangled particles are connected by microscopic wormholes, potentially dissolving the contradiction. Neither has been confirmed, neither has been ruled out. More than 10 years later, there is still no agreement on whether crossing a horizon is gentle or lethal. Somewhere between smooth and on fire, physics still can't tell you which one is waiting at the edge. The unresolved argument over the horizon itself leads to the deepest fracture of all, the one that started this entire field. Number 1. The information paradox. Stephen Hawking wasn't expecting a crisis. After publishing his 1975 results showing black holes radiate and slowly evaporate, he assumed the story was basically finished, a strange but tidy addition to black hole physics. Quantum mechanics carries one rule that is treated as close to sacred: unitarity. The principle that information about a system's exact prior state is never truly destroyed, only scrambled, always recoverable in principle. Hawking ran the numbers on what his own radiation actually looked like. It came out purely thermal, meaning purely random, carrying no imprint whatsoever of what had fallen into the black hole to produce it. If that's correct, then when a black hole finishes evaporating completely, every detail about everything it ever swallowed, every particle, every structure, every bit of information is simply gone. Not hidden. Gone. That directly violates unitarity. Hawking published this formally in 1976 in Physical Review D, Volume 14, in a paper titled Breakdown of Predictability in Gravitational Collapse. In 1997, he made a public bet with Caltech physicist John Preskill that information really is lost. Hawking conceded the bet in 2004, publicly reversing his position, though even his own proposed resolution convinced almost no one. The failure parade since has spanned 3 separate frameworks: complementarity, later shown inconsistent by the firewall argument; holography, which implies information should be preserved, but has never specified the actual mechanism by which it escapes; soft hair, a 2016 proposal by Hawking, Malcolm Perry, and Andrew Strominger in Physical Review Letters, suggesting horizons retain subtle quantum imprints, still unconfirmed. 50 years after the paradox was first written down, there is still no accepted answer for where the information actually goes. If nothing that falls into a black hole can be said with certainty to survive, then the laws you've trusted your entire life may not be as universal as you were told. 10 objects. 10 papers. Not one of them sits at the fringe of physics. Every single entry on this list comes from the exact center of our most tested, most confirmed theories, general relativity and quantum mechanics, sitting directly beside a photograph of the real thing, taken by a global team of scientists who were not looking for a mystery when they started. The universe is not confused about what happens at the edge of a black hole. It knows exactly what happens. We are the ones still arguing, still betting, still publishing failed explanation after failed explanation 50 years into a paradox nobody has closed. The horizon isn't hiding an answer from us. It's showing us precisely where our answers run out. If you want to see more videos like this, click the video on screen now.